So constraint optimization, chapter 15. So today, this is today's topic. Actually, now we are in week 8. So maybe I will correct it later on over here. It should be week 8 only. So this is the lecture 11, or you can also say that it is the 11th topic. So you can see that in this course, there are many topics, relatively small topics, which we can complete in 1 or 2 hours. Okay, so in the constraint optimization problem, our main concern is about a special kind of problem which is called as the linear programming. So in linear programming, we have to maximize or minimize a certain function based on some constraints. And we call it linear because the constraints as well as the function which is to be maximized or minimized are both linear. Okay, that means they have variables which are to the power of 1, like x, y, z. These are the variables. We will not have such variables such as x square, y square, xy, etc. So we will have only variables like 3x, 4x, 5y. So the problem will be linear in nature. And the word programming means it is a method actually to solve this problem. It is not necessarily a computer programming, but it is kind of like a mathematical programming, mathematical method, algorithmic method, which can be applied. And then later on, of course, it's linear, it's computer applications as well. So in this topic, first of all, we will learn about how we can formulate the linear programming problem first, and then we will look at its graphical method, uh, which will help us visualize the problem. That means what are the mechanisms involved and how the constraints come into the picture, and how the constraints bound the solution. And then we will look at one of the mathematical method for solving this problem, which is called as the simplex method. Okay, so after the simplex method, then we will look at the computer application of this method. So we will use the solver add-in to solve this linear programming solution. And then we will also look at its look at the method or the functions which are involved in the which are available in the MATLAB programming language to solve this linear programming solution. So the standard form of a the standard form of a linear programming solution, linear programming problem is that we have a function z, which we will represent by z, and that function sorry. Okay, and that function z have to be maximized. So z is equal to c1 x1 c2 x2 plus c1 xn, etc. Okay, so this c1 c2, these are the constants, and these constants are the payoff of each unit for the jth activity that is undertaken. And x is the magnitude of the jth activity, and z is equal to the total payoff due to the total number of activities. So let's see this with the help of the example in the book. Okay. So as you can see that uh, this is in the standard form of the book. So we have to maximize or minimize a function. So in this case, let's say we want to maximize it. And then we have some constraints on that function. So those constraints will be also involving these x1, x2, xn variables. But these x1, x2, xn variables will be multiplied by some other coefficients. And these constraints will be represented in the form of the inequality. Okay. Uh, so that means ax1 plus ax2 should be less than or equal to ba1, or maybe greater than or equal to b1. Normally we will say less than or equal to b1. Okay. So the constraints are represented by the equality. So there can be one set of constraints. There can be normally we have two or more sets of constraints for a feasible solution. Similarly, we have some limitations, another set of constraints that the values of x1, x2, xn, that is the values of xi, are all equal to 0, which means that we will be only considering the positive value cases. As for most practical problems, and for most production related problems, etc., we always deal with the positive number. So there is no practical way for representing some negative production or negative value produced or negative number of goods produced. Uh, so in this case, we will represent xi is equal to greater than or equal to 0. So this will be another type of constraint. So in very short, what we can say that the standard form of the linear programming problem is involves three conditions. Okay. First is the objective function. So this is called as the objective function. Okay. Z is called as the objective function, which has to be maximized or minimized depending on the type of problem. And then there will be a set of constraints. Okay. There will be a set of constraints, and the constraints are two types. So combination of these different parameters constraint, and the constraints applied on the these individual parameters, xi parameters. Okay. So this is the formulation. This is the brief formulation of the linear programming uh, problem. So let's see it with the help of one practical example. So in this example, we suppose that a gas processing plant receives a fixed amount of raw gas each week. Okay, so you have to read this the problem of this statement very carefully. Okay, so a fixed amount of raw gas is received each week. The raw gas is processed into two grades of heating gas, regular and premium quality. So from one, a raw gas is received, and from this raw gas we produce the regular gas and the premium gas. These grades of gas are in high demand. That is, they are guaranteed to sell and yield different profits to the company. So, however, their production involves both time and on-site storage constraints. That means there are some constraints, time constraints, and the storage constraints. That means we cannot spend more than certain number of amount of time on the production, and then we also cannot store these products on the plant more than some certain amount of more than some certain amount. Okay. So these are the two constraints. So for example, only one of the grades can be produced at a time, and the facility is open for 80 hours per week. So that means if we are producing one grade, then we cannot produce another grade. And that means the total production uh, for both grades can be taken as the sum of the two productions. Okay, production of regular gas and production of the premium gas. Further, there is limited on-site storage for each of the products. So all these factors are listed below. Note that a metric ton or ton is equal to 1000 kilogram. So here we have summarized this information. So if we produce raw gas, then it is about 7 cubic meter per ton. Okay. That means we will need 7 cubic meter of raw gas for 1 ton of production each week. Okay. Similarly, for the production of the premium gas, we will need 11 cubic meter of premium gas per ton each week. But total availability of the raw gas is 77 cubic meter. Okay. So similarly, for the production time, we cannot spend more than 10 hour per ton. Okay. So it will that means for 1 ton of the raw gas production we need 10 hours, and for the premium for 1 ton of production we need 8 hours. But total we cannot spend like 80 hours per week. That means the plant cannot be operated more than 80 hours per week. Okay. So this is another constraint. And the storage constraints are 9 ton and 6 ton. That means the regular product cannot be stored more than 9 ton, and the premium product cannot be stored more than 6 ton. And the profits are 150 per ton and this 175 per ton. That means if we produce 1 ton of raw regular regular gas, we get a $150 profit, and or maybe $150,000 profit, whatever the way, 150 profit. And then for the premium, it is 175. So develop a linear programming formulation to maximize the profits for this operation. So given this information, we have to formulate the linear programming problem. So for the formulation of the linear programming, the first we will formulate the objective function. So for producing the objective function, what we have to consider is that uh, we have to find the production of X regular and premium. That means how much regular we will produce and how much premium we will produce. So assume that, we will assume that we will produce X1 regular and X2 premium. So if we will produce X1 regular, so the profit from regular will be 150 X1. And similarly, the profit from a premium will be 175 X2. So that will be the total profit. So, so for the objective function, then that means if we represent this top profit by Z, so then we have to maximize 150x plus 175x2. That means we have to obtain the maximum values of this function. So without any constraint, we can put any value of x1 and x2 to get the value of Z. That means we will put, if we put higher value for x1 and higher value for x2, then we will increase the value of this Z. But since there are some constraints, so therefore we can only obtain certain value of this maximum due to those constraints. So now let's look at those constraints. So what are those constraints? So in this case, the constraints will be this raw first constraint, second constraint, and then the 4 constraints like this 9 and 6. So for this first constraint, it will be 7 cubic meter per ton. So we are producing x1 ton and x2 ton. Okay. So everything is per ton. So this means that for this uh, resource availability, 7 cubic meter per ton. So 7 times x1 plus 11 times x2 should be should not be greater than 77. So this will be the first constraint. So 7 times x1 plus 11 times x2 should be less than or equal to 77. So this is the uh, second constraint. So 7 times x1 plus 11 times x2 should be less than or equal to 77. So this is the first constraint, not the second constraint. The second constraint will be the production time. So the production time cannot be more than 80 hours. So production time is also with respect to per ton. So it will be 10 times x1 plus 8 times x2. It should be less than or equal to 80. Okay, 10 times x1 plus 8 times x2 is it should be less than or equal to 80. And similarly for the individual storage, this x1 should be less than or equal to 9 and x2 should be less than or equal to 6. So we summarize everything together over here. So first of all, we will have the objective function. And then we have this first constraint, second constraint, and then these two individual constraints. And then another additional constraint is that this is called as the positivity constraint. Both x1 and x2 are greater than 0. Both x2, x1 or x2 should be greater than 0. That means they should have positive values. Okay, that means because since we cannot have the negative production in this case, a negative ton of gas produced. So this has no practical meaning. So the values of x1 or x2 should be all greater than or equal to 0. So we can have the value of x1 is equal to 0, but not less than equal to 0. If value of x1 or x2 is equal to 0, that means no gas produced, which is okay. But a negative value is not acceptable. Okay, so that was the uh, that is how you will set up the linear programming problem. So in the setting up of the linear programming problem, then you set up, first we will set up the objective function, and then we will one by one look at the constraints on that function. So in this case, we have just set up the uh, linear programming function. But the next question is that how do we find the values of x1 and x2? Okay, that means we have these set of equations, and then how do we find the values of x1 and x2? So whether it looks like a system of equations, but it is not exactly like a system of linear equations because it also involves the inequalities, and then here we have some maximize, something like maximize is like that. So by this thing, when we say that it is we have to maximize this objective function, it will mean that it is not exactly like the system of linear equations for which we can apply the Gauss elimination method directly, and then there will be we can expect a unique solution. That is, in this case, uh, we will not have a unique solution, okay? Because it is a maximization problem, which means that any of the value which will be less than the maximum will be also feasible, okay? Will be also feasible. That means that will be also possible, okay? But there will be only one value that will be maximum, and that will be our optimum value. So therefore, in this case, we are looking at the optimum solutions. So as there is no one solution over here. So the optimum solution is the one which is the unique or one solution only. So we are looking at the optimum solution. And in a way, this is different from the solving like system of linear equations. Although we can formulate it such in a way, something like that in the, for example, for the simplex method, that we can deal it in a similar manner as the system of linear equations. But it's not exactly like that. Okay, so do you have any question up to now?
No.
No.
All right. Okay. Okay, so now next we will look at the how to solve this problem. That means, okay, if this is the problem, then what are the values of x1 and x2 that will maximize the profit? Okay, so for this we will start with the a graphical solution. So in the graphical solution, we can see that we can plot these different curves on a paper, and then we can visualize the solution. So a graphical solution. So in the graphical solution, we can plot these curves. So when we will plot these curves, we will obtain this figure. And then you can see that in this figure, we can see a number of different things starting from these numbers. Okay. So what are these numbers? For example, 1, 2, 3, 4, 5, 6. I just need to take a call. Hello?
Yes.
Yes.
Yeah. Okay, so we were talking about this graphical solution. So this graphical problem we can set up by ourselves. So these 1, 2, 3, 4, 5, 6, they represent the constraints. Okay. So let me show you over here. Maybe I can set it up on Excel. So in Excel, okay, we can set it up. So for example, it is the same example for which we have formulated the solution. So for the graphical solution, we have this this set of equations. So we can uh, we can number these constraints. Okay, these 6 equations. So 7x1 plus 11x2, and then similarly this. So in this case, we can get 6 equations, and then we can plot these equations on Excel. So we can say that these numbers are x, so something like this, x1 and x2. Okay. So for example, um, we can plot these values over here. So for example, if we have this first equation, 7x1 plus 11x2 is equal, less than or equal to 77, we can represent it in the form of an equality. So just say that if we take x2 over here, and then we will bring everything on the other side, so we can represent x2 is equal to minus 7 by 11 x1 plus 7. Okay, so maybe we can take like this. Okay, so for example, if we have like this, so we take some different values of x1. So for example, 0, 0.5, okay, something like that. Okay, and then okay, maybe this many values of x1, and then you can say that it is equal to minus 7 divided by 11 times x1 plus 7. So these are the values of x2. Okay, so this is for the first case. And then another value of x2 will be from the second equation. 10x1 plus 11x2 minus less than or equal to 80. So this can be represented as like okay. So if it is, for example, if it is 10x1 plus 8x2 equal to 80, okay? It's just for the time being, forget about less than or equal to 80. So x2 will be equal to, x2 will be equal to, 8x2 will be equal to minus 10x1 plus 80, and x2 will be equal to minus 10 by 8 plus 80 by 8. So it will be x2 will be equal to minus 5 by 4 plus 8 x2, 5 by 4 x2. Okay, so then we can represent like this. Okay, that is for the second condition, x2 will be equal to minus 5 by 4 x2 plus 10. Is it, can we represent it like this, minus 5 by 4 x2 plus 10? So because you see that the second equation is this.
Okay.
Yeah, second equation is this. This is the second equation. So can we represent it like this? Minus 5 by 4 x2. That is x, we take it over there and then divide it by 4. So it is 10 by 8 is 5 by 4. Okay, minus 5 by 4 x1 plus 10. Okay, and then 80 divided by 10 is 10. So it will be, sorry, x1. Okay, so for the second condition, that is x2 is, this we can say it as x2 dash 1, and then this we can say it as x2 dash 2. Okay, so now it will be minus 5 by 4, minus 5 by 4 times x1 plus 10. So it is this. Okay, so we have these set of values. And then the second one is what? The third equation is what here? X1 is less than or equal to 9. So this is equal to x1 is equal to less than or equal to 9. Okay. So for any value of x2, x1 is equal to 9. And for any value of, and x2 is less than or equal to 6. So these are some some of the values which we can plot on the graph. So what we can do is we can now plot these two values. Okay, so insert. Where is this? I want to insert the chart. So where is this chart? Yeah, here. Insert the chart. Okay, and then what type of chart I want? I want the bar chart. No, I want the XY plot. Okay, XY plot, and then I can have like this kind of plot. Okay. So I have this kind of plot, okay, over here. And so this, so maybe I can have something like some more values over here to show it. Okay, that so that I can plot it well. Yeah. And let me plot it some more values so that everything goes to 0. Okay, yeah, that seems fine now. So now instead of this, I plot this value. Okay. Insert this plot. Here. Yeah, so I get this this chart over here. So in this chart, you can see that the values have been plotted on this x-axis. Okay, this is the x2 axis. The vertical axis is the x2 axis, and the horizontal axis is the x1 axis. So there are two x2 axes, and then here you can see that we are obtaining these values. And now what I can do is I can insert some shape in the form of some line. Okay, so maybe I can have a horizontal line. Okay, let's make it a little bit thicker. So I have this horizontal line, or maybe I can also have one vertical line as well. Let me show you why I'm drawing this horizontal and vertical lines. So this is almost a vertical line, and this is almost a horizontal line. Okay, so I can use this horizontal line to represent y, that is x2 is equal to something. Okay, so let's represent x1, and the vertical line I can represent to show x1 is equal to something. Okay, so here is what is the condition over here. X1 should be less than or equal to 9. So this will be represented by vertical line. Okay, so x1 is less than or equal to 9. So where is this? So this line represents x1. So I can use the left and right arrow to move left and right. So here it will be like something like equal to 9. Okay, so this means this line row shows x1 is equal to less than or equal to 9. So any solution will be, any constraint will be towards the left of this value. And similarly for this line represents this second curve, and any of this solution will be towards on the lower side of that. And for this line represent the x2, that is the first constraint. Any of the solution will be towards on the lower side of that line, okay? And now let's represent this one. So this one will be x2 is less than or equal to 6. Okay, this is the horizontal. This will be represented by the horizontal line. So x2 is equal to 6. So where is x2 is equal to 6? Yeah. So 6 will be somewhere here. Okay, here. So this will be a line. So this means that we will get a point over here, a point over here, and another point will be here. Okay, one will be this point, and the for these like this, for x1 is equal to 0 greater than 0, so this x1 is equal to 0 and x2 is equal to 0, we will respectively get the x and y axis. So that means the feasible area will be here. Okay, that is the the feasible area. Okay, so feasible area of the solution will be this one, starting from this point. Let me draw it. The feasible area is insert a shape and insert a what? Yeah, maybe a free form shape. So in feasible area will be like this, starting from this point to here, to here, and then here, and then up to here. So this will be the feasible area. Okay. So that means anything, any solution should be within this feasible area. So for this feasible area, then what we have to find is the what we have to find is the optimum solution. So for the optimum solution, we have to look at the this objective function. So this objective function z is equal to 150 x1 plus 175 x2 can be represented as, so of this objective function, z is equal to 150 x1 plus 175 x2 can be represented as like this. So for example, if we take it in terms of x2, x2 is equal to minus 150 x1, right, divided by 175. If we take the value of z is equal to 0, then it will be like that. Or if we take any other value of z, so then it will be, for example, it will be minus z divided by 175. Okay, so since the value of z can be a constant, 0, 1, 2, 3, any value, okay, and for any value of z, if we will plot this function on this chart over here, if we will plot this function on this chart over here, the all these values, all these lines will be parallel with each other. Okay, so for example, if we plot for z is equal to 0, then what will be the value of x2? So in this case, what we can do is I can just this is for the x2 for the maximization problem, or for the objective function. Okay, for the objective function I can plot. So it is equal to What value? What is this value? So this value will be equal to this value will be equal to minus 150 by minus 150 divided by 175 times x1, okay, times x1. So which is this? So this value. Okay, and then what will be its plot? Okay, so the value of this plot will be, so it will be also a straight line. Okay, so for example, what will be that straight line? So maybe now I can plot another. Insert this chart. Insert this chart here, this one. So what is this line? This one. This is the line. Okay. So let me put this chart over here. And I manually draw one line. Where is this line? Insert. Okay. I manually draw one line over here, which is almost parallel to this line. That is, this line is almost parallel. You see, this is almost parallel to this line. And then I take this line to the upper chart over here. Yeah. Okay. So now I can see that I can move this line, for example, which I have drawn for the objective function. I can move this line up and down over here. Why I can move this line up and down? Because we can see that with any value of z, the plot of this function will be parallel to this line, right? So now what I can see over here is that here this plot is representing, is touching this area at this point, okay? But this is the, at this point, there is the value of x is 0, 0, the value of x1 is 0. And the value of the objective function will be also 0. But this is definitely not the maximum point. If we want to obtain a maximum point, so I have to move this line up. So when we move this line up over here, this line is intersecting this objective function at various points in these various areas. But when I move this point line further up over here, at this point, it is only touching at this point over here, okay? And for any point above, it is touching more than one points over here. So there is no feasible solution. Actually, this, yeah, maybe I can just shape, format the object. There is no fill. Okay. So now it will be better, I think. Anyway, we can. Yeah. Okay, I have put as a rand delayed wait also. So this, you can see that at this point over here, it is passing through this objective area. So that means there are various points in which it is possible, but only at this point, that is somewhere here, it is touching in this shape at only one point over here. So that is the optimum solution. Okay. So let me go back to this the graphics which is plotted over here. This graphics has been plotted better because I did not choose the scale equally on both axes, so that's why the shape was not looking very well. But here it's relatively easy. So if you will plot a line parallel to that, this parallel line, which will be representing the objective function, will only connect at this corner point. For all other positions, it will be passing through the objective function, and there will be more than one number of points. So it means that there will be more than one solution. So the most, that means in this case, for the graphical method, as we can see over here, for the graphical method, and this, as we can see in this figure B, the optimum solution will be the one which will be at one of the corners of this feasible area. Okay, which will be at one of the corners of the feasible area. So that means in this case, for our later search of the solutions, we can find the solutions only at the corners A, B, C, D, E. So A, B, C, D, E, these are the 5 corners. So one of the corner will give us the optimum solution. So, in this case, this optimum solution is obtained by this point C. But if the if the slope of this maximum, that is the objective function, is something like different, so then that solution can be different as well. So, for example, for some shapes we can get the solution at point D as well, and for some cases we can get the solution at point B or E as well. So depending on the slope of this curve, okay. So if you go back to the Excel, and if I, for example, if I plot it on a equal scale on both sides, then it will be much easier to see it. So, for example, if I change the shape of this, for example, if I change the slope of this line, and then maybe we can get the solution somewhere here. Because now, or maybe we can get, for some other shape, we can get the solution somewhere here as well. Okay, so the slope of this objective function also has effect on the solution. Okay, so this we can also see it in the numerical solutions as well. Okay, so that was the graphical method. So thus you can see that, let me read it over here. Thus, increasing the value of the objective function moves the line away from the origin. Because the line still falls within the solution space, our result is still feasible. So for the same reason, however, there is still room for improvement. Hence, Z can keep increasing until a further increase will take the objective beyond the feasible region. So as shown in this figure 15.1b, the maximum value of Z corresponds to the approximately 1400. So at this point, x1 and x2 are equal to approximately 4.9 and 3.9 respectively. So thus the graphical solution tells us that if we produce these quantities of regular and premium, we will reap a maximum profit of about 1,400. So just as like this. So for this values, for this point, we have the values of x1 and x2, and these values of x1 and x2 will be put into this objective function that will give the value of z is equal to about 1,400. Okay, so aside from determining the optimal value, the graphical approach provides further insights into the problem as well. And we can also input these values of x1 and x2 into the constraints, and then we will see that some of the constraints will be fully met, but some of the constraints will not be fully met. So for example, the constraints of storage and time in this case are being fully met, but these constraints of the constraints of what were the constraints? This was the time constraint and the material constraints. Okay, yeah. So the time constraints and the material constraints are the fully met, but the storage constraints are not being fully met. So therefore, some of the, it is not necessary in this optimization to meet all constraints, okay? To meet all constraints. So some of the constraints will be met, but some of the constraints will not be met. Okay, so let's stop at this time, and next in the